Hello, everyone. Can you hear me?
Yes, sir.
Good, good, good. Welcome to day one of Ignite. Is everybody having a good time?
Yeah.
Down in front, we're excited. So I have to warn you, you guys in front, this is like SeaWorld. You guys are in the splash zone. So as soon as the drone takes off, you guys may be in trouble in this front row. So the drone we're going to talk about today, or the one that I've been using as an example, has anybody seen this drone before? This drone is by a company called Ivify. They normally make racing drones. This one is a research drone. I have it over at the booth, so you can come look at it. We have some lights that I put on here. These are navigation lights that are required by the FAA if you want to fly at night. These are actually pretty amazing because when you actually turn them on, they actually get really bright. And this will allow you to do things like fly at night or fly in inclement weather and things like that. So that's this drone that we're using. And you guys can come take a look at it. It has some components in there that we're going to talk about. It's running things like a Jetson TX2 board for inferencing on board, so you can control and do the inferencing directly on board. So we'll talk about that in Jen. So again, my name is Paul Stubbs. I'm Director of AI Marketing at Microsoft. I'm responsible for things like autonomous systems. If you haven't been at our booth over here, we actually created a hockey bot. I took a high-speed industrial Delta robot and we turned it into an air hockey table. So that's a lot of fun, so go take a look at that as well. But really what I want to talk about is around drones and how do we go from where we are today to where we're trying to get to, which is the world of autonomy. And so today things are automated or in many cases manual. So in the case of most drone flying today, you have somebody that's flying the drone, and that drone is doing whatever it's doing, taking pictures or video, and then later you come back and you download the video and you store it someplace, and you may look through the video and you may say, oh, there's something wrong there, and that's the process today. What we want to do is make that autonomous, make that to be able to not only fly the missions autonomously, but to be able to understand what it's seeing, like, oh, there's a broken capacitor or a crack in the bridge, or the road is not correct, or whatever you're inspecting. You want to be able to do that autonomously. And so what we want to do is understand all the pieces on how you build this. But even more so, another interesting piece which is really valuable is that this is really a monumental shift in history that you guys are experiencing this week. And what's happening is that we're working with the FAA, and part of the FAA, what's going on is that, as you know, there was some recent issues with some of the Boeing 737s, which caused the FAA to go back and look at the process on how aircraft are certified. And what you may know as drone pilots is that there really is no certification process for drones. Now, if you're doing commercial drone flights, you need to have a remote pilot license, an FAA 107 license. How many people have that? So a few guys over here. So if you're doing any commercial flight at all, if you're taking the drone out, flying it around the parking lot for your company, according to the government, you need a license. And it's a simple license, it's just an exam, and you can take that. But what it tells you is there's lots of things in there that you can't do. So for example, you can't fly over people, ever. You can't fly at night. You can't fly beyond line of sight. You can't fly over 400 feet above ground level. So on and on, there's a lot of rules and things you can't do. And the reason is it's kind of, whenever new technology comes out, the government just says, okay, nobody can do anything until they figure it out, and then they start loosening up the grips. Well, this moment is when they're starting to loosen the grips. And what they're doing and what we're working with as Microsoft as part of that is that they've come up with a new process. And this will probably be announced by the FAA probably in the next few weeks and be put on their public site for public review. But basically, they're moving from a system of certification that caused the issues with Boeing, which is, here's some code, I'm going to certify every line of code, now don't touch that code, it's certified. Well, the problem is, it's expensive to recertify the code, so most airlines don't certify the code, they just patch it. And eventually you get so many patches, you sort of lose control over what's going on. And so the FAA said, hey, in the modern time, we need a different modern process. And so what they're going to announce and what we're following is to certify aircraft based on performance. So you certify what the aircraft can do, not how it's written. It's sort of irrelevant what the code is. But as part of that, through AirSim and our simulation tools and the stuff that I'll talk about today, the Dronecode stack, that will be certified, and that'll be the first certified aircraft, which is 3DR HG520. That model aircraft on the Dronecode stack will be certified. And what that means is once that's certified, it behaves just like any other aircraft. It'll get a November tail number. It can fly over people. It can fly at night. It can do all these things that you today need a waiver for, or you can't do at all. So it's really going to be, it's really a monumental shift in the way that aircraft are certified, starting with drones, and you'll start seeing it trickling up to manned flights and things like that very soon. So this is why this talk is so important, is because it's really going to be a groundswell or different way that we do things using this Dronecode stack. How many people are familiar with Dronecode? Nobody, good. So in the drone world, there's two sort of camps. There's the Android and the Apple camp, right? There's the walled garden and the wide open source kind of thing, right? So DJI, you can kind of think of analogously as sort of the Apple walled garden kind of camp. They have a lot of great stuff. It's really amazing, but it's sort of closed and you have to follow their structure. On the other side is the Dronecode camp, which is top to bottom, a Linux Foundation project. It's an open source stack, and everybody's participating in that that's not DJI, right? And so these are the two worlds, and the FAA is certifying the Dronecode stack. And for various reasons in today's political climate, they're not certifying the DJI stack, right? And so this way, if you want to do anything with public sector, government projects, anything to do with that, then the Dronecode stack is how you do that. So let's take a look at that. So in Dronecode, and in the same way as DJI, these are sort of analogous. So if you're familiar with the DJI stack, this is exactly the same. You really have sort of three buckets of things when you're programming drones. You have stuff that runs on the drone, we call the flight controller. And in this case, the flight controller is by this API called PX4. PX4 is the standard flight controller. Now you can run that on a lot of different hardware. The hardware that we'll run it on is called Pixhawk. Think of it like a Raspberry Pi, if you will, right? So the Pixhawk controller runs the PX4 API, and that's your flight controller. And that controls the basic things like how fast the motors turn, and how does it compensate, GPS loss, and how does it communicate with the radios, and all the basic flight control stuff is part of the flight controller. And then you have the ground control station. So in that picture, when we had the farmer controlling, he's the ground control. So normally that could be your Windows machine, it could be an Android or an iOS tablet. It's something on the ground that is running software, which we call QGroundControl in this stack, which is doing mission planning. And the ground controller communicates to the flight controller using a communication protocol called Mavlink. So those are the three kind of big buckets. Now you can also have, and what we'll show on the next slide, is an architecture where you have, well, I want to run some other code on the drone that's not necessarily the kind of the heartbeat or the flight control, like inferencing my images or looking at video or telling the drone where to fly next, right? And so in that case, we run what we call a companion computer. And the companion computer can run anything, but in general, we run ROS, which is the robot operating system. Because in the end, a drone is just a flying robot, right? And so if you think about it from that analogy, then the way that you program robotic systems like a drone or a car or an arm or the Delta robot we have over here is relatively the same. And so we run ROS on a companion computer. And in this case, on this device, we're using a Jetson TX2 board from NVIDIA. Then we have the ground controller, which in this case we're running Windows with QGroundControl on Windows. And that communicates through Mavlink to the flight controller. So that's the stack. Is everybody with me? So here's sort of the kind of architecture diagram of how that looks. So everything above the line is stuff that's flying in the air. Everything below the ground is stuff that's happening on the ground. So if you're generally putting kind of your logic in your head as a developer, you're thinking, well, okay, this is sort of fixed. I can't really change this. This is sort of the core of what's happening. I shouldn't touch this stuff, although you can, it's open source. It's running on some hardware. In this case, Pixhawk 4 is the hardware. We have another computer on the drone, in this case a Jetson board, and we're running ROS, the robot operating system. And we're running ROS2 because ROS2 supports DDS from OMG. And DDS from OMG allows us to talk fast RTTPS, which is what Pixhawk natively talks. So it becomes very easy to communicate through these two, and they're connected through, normally via a wire, which is UART, right? Old school kind of CAN bus stuff. And then on the ground, we run the ground control. This can run on Linux, Mac OS, or Windows. It's extensible through Qt, so Python Qt applications. This whole thing's open source as well, so if you wanted to extend it, you could. And then we talk Mavlink, which is the communication protocol for radios to the drone itself. And then you could also, if you wanted to, run anything else on your ground control you want to, like maybe another ROS instance that's then sending stuff to the Azure cloud to do further inferencing on images that are sent down, right? So maybe you do some preliminary processing on the drone, and you do deeper processing, through the cloud, through your ground controller. So that's sort of the architecture stack. Excuse me. So here's a drone that I'm building at home. This is an S550 frame, which matches a DJI Matrix frame. We have 6 things. This is what the Pixhawk looks like. So on the Pixhawk here has all these components, and you plug in your radio, which then connects to the radio plugged into your ground controller. And so that's how they communicate physically. We have a companion computer. In this case, this is not the Jetson TX2. Does anybody know what this is? This is the new Jetson Xavier. This is about 10 times faster than the Jetson TX2. So this is an awesome computer. And then we have GPS, so that's a GPS controller. This is the power distribution board here, so we're doing distribution power. And we distribute the power to all of the motors. And the motors are all connected to an ESC, which is electronic speed control. So this controls the speed of the motors. And then all of those get communicated through your flight management unit and so on and so forth. So that's generally the architecture for how you build these drones. But what we really talked about here is really just one part, right? When you saw the guy flying the drone in that first picture, there's really today 2 ways people are doing things. They're manually flying the drone, and it's basically just a flying camera. They fly it out, they take pictures, they come back, and they download the pictures. They plug the drone, download pictures. And then, so there's taking the picture. So there's 2 aspects of autonomy that we want to deal with. We want to deal with autonomous flight, which is, can I just fly the mission by myself? Can I just send the drone out and map all the hotspots of the fire, or map my field, or count the train cars, or whatever? That's the autonomous flight part, so that's one problem. And then I say, well, I want to do vision, so I want to autonomously flag or understand when things are wrong while the drone is flying. I don't want to wait to download it and then the next day, try to process that. So that's the vision part of that. But there's a lot more. If you're going to build an actual drone solution, there's more than just how do I get it to fly, which is sort of the architecture I showed you. But it's how do I plan the mission? How do I know where to fly, when to fly, what the heights and altitudes, and how do I go around objects, and how do I avoid things like power lines or trees or things like that? So that's mission building. There's vision. This is where we're really strong at. We have lots of stuff around cognitive services, machine learning can help you with vision. And then these other pieces which are important as well, which is management, reporting, how do I securely deploy the code? How do I update the code, right? These are all in the kind of the Azure IoT space, right? How do I then debug it? How do I do DevOps to do continuous integration? This is all this space here. And then there's potential to do mobile applications to build your ground controllers, or to build companion computers that you can follow along with the mission. And so there's this whole sort of end-to-end problem as you're building a full solution that's not just about how do I fly the drone. It's a much larger space. So in this case, let's take a look at this example here. In this case, I'm running 2 instances. I'm running the flight controller in a Docker container. So I'm running it in software in the loop, we call it. And I'm running the ROS node as software in the loop. So that's simulating the hardware of the flight. This is QGroundControl, where I'm actually loading a mission. I can load the flight mission here. These are the waypoints that the drone is going to fly. We can then upload that mission to the drone. That then uploads those waypoints to the drone automatically. And then we can actually start the mission here, which then sends the control to the drone saying, hey, start your mission. And it's going to fly. This is AirSim, if anybody hasn't seen AirSim. So AirSim will give you high fidelity images using the Unreal Engine. and then you'll be able to simulate, and what we're doing here is, excuse me, inferencing. So as the drone flies, every time it finds something, we flag it and we can highlight and with a box what the object it found. In this case, we're looking for cars. And so every time we find a car on the map, we'll flag it so that you, using this application on a computer, right, this is that piece I talked about, you can then decide what you want to do. Do I want to change the mission because something's wrong? Do I want to continue? Do I want to alert somebody? Here you can see we have sort of, we can flag it through the normal kind of AI vision process and see that. So here, in software in the loop, without having a drone, you guys can start and do all of this today with just a Windows PC. It's all open source so to get started today. So it becomes very easy to then plan your missions, fly your missions in simulation, which is what we're showing the FAA to certify, saying, hey, you can certify this because I've flown it 4,000 hours in simulation, right? This is the process the FAA is talking about. And this is how you do that, right? We fly it in AirSim. We can do our vision stuff here as well. This is a custom application we wrote. This is basically reading the messages from ROS that are coming out of the robot operating system, and we're displaying it on this web page that we created. So that's the sort of stack that you do that. A big component of this is AirSim. AirSim, as you saw in the keynote video for the DARPA challenge that we helped them build, we actually simulated the entire tunnel for the DARPA challenge for Carnegie Mellon University so they could actually fly the drone ahead of time. But one of the things that's important is I said that drones are just robots too, because in this requirement from the government for the DARPA challenge, you had to go into the tunnel for 90 minutes. Well, most drones don't have batteries more than 10 to 15 minutes. So what they did was they created the ground vehicle that you've seen in the videos, and the drone actually sits on the ground vehicle like a battery charger. It drives along together until it sees something interesting, it launches the drone and looks for it, comes back and charges. So now we have robot-to-robot communication and coordination of robots. So that's why ROS being the common component makes it very easy to do those things together. And so this is the vehicle. So here was the ground vehicle, and here was the drone. You can see they're using an Intel PrimeSense 435i camera here, and they have things like LiDAR here and stuff like that. But this drone will land on the ground vehicle and communicate with that. In AirSim itself, just briefly, we can simulate sensors. So here are 3 sensors here. We can see the different light, we can see infrared, and we can just see the actual visual. So you can simulate any sensors that you want to with an AirSim. So if you have some sensor like a LiDAR or maybe GPS, you can simulate that. You can create any environment. It's just a simple Unreal Engine. So anything you can do in Unreal, you can do in this environment. So you can, what we use it for is we actually train the vision models using simulation, and they're good enough that when they see those objects in the real world, they can identify them. So if you had something like a car or a broken capacitor or different lighting or weather conditions, you can simulate all of those before you actually get out into the field. So the kind of the brains behind this is one of the things that I think Satya talked about this morning, which is around machine teaching. And machine teaching is a new piece that we're working on. You can sign up for a limited preview now if you go to aka.ms/as. But machine teaching is at its core around reinforcement learning. And reinforcement learning is a different type of AI modeling, different than machine learning, where machine learning learns from data. Reinforcement learning learns from experience. So in machine learning, I've had 10 years of bank records. I could process those and find fraud and create a model. But with reinforcement learning, I need experience. I need to actually do something. Well, the way that I actually do something is in a simulation, right? Because I can simulate anything and run for thousands of hours. And the problem with running things in the real world is in the real world, 1 second equals 1 second. So if I have to process for 10,000 hours, it's going to take me a long time. In simulation, I can run those in the cloud at scale and parallelize those and do it a lot faster. So this is what we're doing. So in here, we can have expert do machine teaching. He can create a model, which we call Inkling. It's a language for programming machine teaching. Then we can use simulation to test those hypotheses with machine learning. We can then evaluate, send the reward back. This is the typical machine reinforcement learning loop, if you're familiar with that. And then once we're done, we can actually deploy that model to the real end device, the drone in this case, and we can actually do that physical detection. But like I showed you earlier in the talk, is more, there's the whole end-to-end. There's flight, there's vision, there's management, there's mission control, there's reporting, there's telemetry. That's where the rest of the Microsoft platform comes in, right? It really takes a village in this case to build a real end-to-end solution. And we have all of those pieces available to us, from IoT to data storage to video storage and AI processing. All of those elements come into play as pieces to building your drone solutions. So with that, here are some links for you. Also, come over to the booth. I have a few drone books here. So one of the things the FAA required, if you fly a drone either commercially or not commercially, you're required to log all of your missions. So when you do, if you have an accident, and the FAA comes and says, well, when did you last rotate your propeller blades? You can say, I don't know. And they say, how long have your batteries been operating? You can say, I don't know. Or you can say, I have it in my log, they've been and then they go away and leave you alone. So these are actually really great books. They're just a log book. I also have a checklist, because the FAA will say, hey, did you check the batteries before you flew? Did you do this? And you say, yes, I did. I went through my list. So this will help you keep you safe, if not avoid lawsuits in the future. So I have a few here if you want to come grab one after, and I have more at the booth later if you're interested. And so I think that's all I've got. Thank you.